Namaste. Welcome to this channel Dr.ARM's chemistry. Friends, we were discussing last time this electronic spectrum with respect to this ligand-field transitions. So this part is also continued in this lecture. So in continuation with this, we will see the various spectroscopic terms and the transitions of electrons with respect to the ligands. So here we will see that the spectroscopic terms are arising from the distribution of electrons in various orbitals. In case of transition elements, we know that the orbitals, d orbitals are like this. So these are T2G orbitals and these are EG orbitals. So each orbital is T2G in nature, and in case of, if you consider the D3 configuration, for which we can have 3 electrons, and these 3 electrons can be moved in the EG orbitals from T2G orbitals. So these electrons are to be moved or excited to the higher energy level. So after excitation, the electrons, one of these electrons, say this electron is moving to this each orbital like this. So we can get the next situation, or alternatively we can have the distribution like this also. So out of these orbitals we can have the 2 electrons in T2G and 1 electron with the opposite spin. So these are variety of, means there are such type of excitations. So each of these 3 orbitals is called a T2G orbital, that is triple degenerate orbital, and each of these orbitals is called a double degenerate orbital. So depending upon the distribution of electrons, the transition may be allowed or spin allowed or spin forbidden. So the symmetry of these states is AG symmetry, that is A to G symmetry. The symmetry of each of these is called A to G symmetry, and each electron is denoted by this A to G term. A to G term. So such transition is, so this transition is called a spin allowed transition, and this is called a spin forbidden, because the spin is opposite, and because of this the symmetry is changed, and because of this the transition is not allowed, means it takes place but with very weak absorption band in the spectrum. The T2G orbitals shows that the C3 rotation, these orbitals shows that the C3 rotation of the octahedral point group transfers the product into T2G into T2G into T2G. So this shows that the T2G orbitals are transformed into in this way into itself, and that is called asymmetry. So this is called asymmetry. Then if you see the similarity or symmetry, means all these three orbitals have same symmetry, that is called even parity. So each orbital has even parity, and they are represented by the symbol G for grade. So when the C4 rotation in the direction of z-axis is allowed, and when the rotation is carried out through 90 degrees, then we observe that the symmetry is changing into different ways. So when we are having the three different types of orbitals, see, that is, we will show here dxy, dyz, and this is the dzx. So each orbital rotates in specific manner or in different manner. So out of this, it is found that the dxy orbital, we show here, that is C4 rotation. C4 rotation shows that when dxy orbital undergoes rotation, it shows change in the sign of wave function. It undergoes change in sign of wave function. And as a result of this, we get the negative of the same orbital. So this orbital is also converted into dxy orbital, but the signs of wave functions are negative. Means when the orbital here, it is having lobes which are having their positive signs, it becomes here with negative signs. So the signs of wave functions are changing. Means here the positive signs are changed into negative signs, and negative signs of lobes with negative signs are changed into positive signs. Means the orbital, after undergoing C4 rotation, is changed into its negative structure or negative signs. But the other orbitals, dyz and dzx, dyz and dzx, shows that when this undergoes C4 rotation, it is converted into the dzx orbital. It is converted into zx orbital. Means after undergoing this orbital, after undergoing C4 rotation, the orbital is changing into other orbital. Similarly, when this orbital undergoes the C4 rotation, it also gets changed into dyz orbital. So that can be reflected by using, or we can see in the form of diagrams. So here we will show the this is the cube, and we will show so these are the phase centers. Now this will be the center of the cube. Now I will show the different orbitals. So this is, we are showing this dxy orbitals. dxy orbitals. It has lobes. This is the dxy orbital. So these two are having say plus sign of wave function, and they are having negative signs of wave functions. So after undergoing a rotation, before rotation, after undergoing C4 rotation, we find that change. We find that this lobe is coming in the position of this lobe, and this lobe is moving in this direction. So if we move this z-axis, so if we rotate this through 90 degrees, so equal rotation through 90 degrees, so the lobes are moving in this direction. So this lobe will move in this direction. So the lobes are moving in this direction, and we will get new position like this. So the center will be located here, and we are having lobes like this. So I will show these lobes. The signs of wave functions, as we have seen that these are plus and these are minus. So they will change here like this. This will be minus, this is plus and minus. So the orbital remains the same. Like this. So this orbital is also dxy. This is also dxy. This is also dxy. But after there is change in sign of wave functions. With the orbital dxy, after undergoing 90 degrees rotation, it will change into itself, but with change in sign of wave functions. Then next we will see. Now we will see other two orbitals, that is dy z changes into dzx after 90 degrees rotation. There is the center of this nucleus. Now this is, we know that rotation of 90 degrees will have the change like this. So after 90 degrees rotation, so this orbital becomes dz because it has lobes between x and z axis. So in this way the signs are also changing. So this plus becomes minus. The signs are also changing. This becomes plus, plus and minus, minus. So you will find also there is change in the sign of wave function. So as a result, we can say that after undergoing rotation through 90 degrees, the dyz orbital changes into dzx orbital, and this dzx orbital can change back into, after the same 90 degrees, into dyz orbital with change in signs. So this type of change is observed. Now in such case we can show that when electron is moving from this dyz, electron is excited from dyz, it is very close, so it requires very few amount of energy for carrying out the transition of electrons, and therefore such type of orbitals are associated with the spin forbidden transitions. So it is more difficult to establish the term symbols for such type of shapes of orbitals or types of orbitals. So when we consider the quartet, T2G to EG1, then this is excited configuration, and it can be shown with the symbols such as 4T2G and 4T1G. So it can be shown with such type of. Here we know that this 4 indicates this 4 indicates a spin multiplicity. Spin multiplicity. Spin multiplicity. This T1 is considered as the spectroscopic state. This is spectroscopic state, and these are electronic states of the atom. Here the term A2G is associated with these characters. So these are associated with these A2G. That is A2G, A2G. Means having same parity. So here the transitions which are taking place within same parity, that is G to G or U to U, are spin forbidden whereas the transitions which are taking place with or between the G and U are being allowed. So in this way, the transitions can be considered here. Now we will stop our discussion here, and in the next lecture we will see what are the microstates from which the spectroscopic interpretation is made. So till then, goodbye, see you next time. Please subscribe to this channel if not, and press the like button and bell icon. So thank you very much for watching this.